Today I want to talk a little bit about the difference between molarity or molar concentration and molality or the molal concentration, which is something that always flummoxes students a little bit because the terms are just so dang similar. So let's talk a little bit about them and how we can convert between them. So molarity should be a little more familiar if you've studied some chemistry because that's our usual concentration unit. It's the number of moles of solute per liter of solution. And remember, solutions are made up of two parts, the solute, which is the thing that's being dissolved, and the solvent, which is the thing that you're dissolving into. So molarity here is a big capital M, and so you can have a solution that's like, 6.0 molar sodium chloride, for example. And that means that I have 6 moles of sodium chloride for every 1 liter of solution. So that's what that tells you about that. So this would probably be an aqueous solution, and we would indicate that the solvent there is water by saying that it's aqueous. It could be dissolved in something else, but let's just for our purposes go with that. Now molality, the mole part implies that we're still dealing with moles, and anything dealing with a how much or how many kind of question for scientists, especially chemists, think about things in terms of moles. So we're still talking about moles of solute, but instead of being per volume of solution, we now have per kilogram of solvent. So of the thing you're dissolving into, for every 1 kilogram you have, how many moles of solute do you have? And this ratio, this concentration, is called the molality. And that molality is symbolized with a lowercase m that is italicized. So this M would be in italics, which is hard to do when you're writing in script, right? So my handwriting on a good day looks like it's italicized, right? But it's hard to indicate that something is actually in an italic font. So the way that we do that when we're printing is by underlining it like this. So this underlined M here indicates that it's in italics. And so I'd have something that looks like this, 1.7 molal solution of, whatever it is that we're talking about. It could also be sodium chloride. And what that would indicate is that I have 1.7 moles of sodium chloride for every 1 kilogram of water. Okay, so that's the way that we're unpacking that there. It's the number of moles of solute per kilogram of solvent. Okay, so kind of wacky. Now this is really useful with dilute solutions. They tend to be sort of similar numbers in that case. But when we're talking about molarity and molality, molality becomes super important when we get into what are called colligative properties, which are properties that change with the concentration of the solution. So how things are affected by a greater amount of solute. And molality comes more into play for that. So let's talk about how it relates as a unit in this video, and we'll talk about how we use it in calculations for colligative properties, which are dependent on the concentration of the solution in future videos. Okay, so let's jump right into the math then. If I have a solution that's made from 5.67 grams of glucose in 25.2 grams of water, what is its molal concentration? And again, you have to be really careful here because as chemists, we've been training you on molarity, molarity, molarity. Now we're asking you for molality. And it's a very small difference, but it's a very important one. So let's think about our glucose here. So if we're trying to figure out molality, we need moles of our solute and we need kilograms of our solvent. So in this case, we look for which one there's less of. That's our solute. So that's our glucose. So our 5.67 grams of glucose, we're going to have to get into moles. And then the 25.2 grams of water, we're going to have to get into kilograms. Okay, and that's going to give us molality, right? So our solute needs to go to moles, our solvent needs to go to kilograms. So the way that I do that then is I need to figure out, in order to get to moles, I need the molar mass. So glucose's chemical formula is C6H12O6, which has a molar mass of 180.2 grams per mole. So we'll start there with our 5.67 grams. And then we have 180.2 grams for every 1 mole of my glucose, which gives me 0.0315 moles of glucose. Okay, and now I need to get to kilograms. So grams to kilograms, there's 1,000 grams in a kilogram. So I'm going to go 25.2 grams times 1,000 grams, 1 kilogram. So I'm dividing by 1,000, so I'm thinking about moving my decimal point, and that gives me the 2.52 times 10 to the negative second kilograms of my water. And now I take the moles of my solute and put it over my kilograms of solvent, and that'll give me my molality. So my molality here is going to be equal to 0.0315 moles for every 2.52 times 10 to the negative 2 kilograms. And that gives me 1.25 molal C6H12O6. Okay. So there's a lot of pieces of information that you're getting from this symbol then. So it's a 1.25 molal solution of glucose. And what that tells me is that for my glucose here, it's an aqueous or aqueous solution, which means that my solute is my glucose, my solvent is water. That's what the aqueous means or aqueous means. And that there's 1.25 moles for every 1 kilogram of water. Okay, so that's how you calculate just the molality, so long as you have some information about what your solute and your solvent is. Now we can go back and forth between the different concentration units. So in a past video we talked a little bit about mole fractions. So let's go from mole fractions to molality then. So if I look at my mole fractions, 25% of my solution is methanol, 75% is ethanol. So the first thing I need to do is figure out which is my solute and which is my solvent. So my solute, in a solution where they're both liquids, which in this case methanol and ethanol are both liquids, they're both really volatile liquids, they're alcohols. So, you know, you can think about the smell of alcohol. Even though they have strong intermolecular forces because of the hydrogen bonding, they're still more volatile than, say, water, for example. Okay, so the solute is the one that there's less of, so that's going to be your methanol. And your solvent is going to be the ethanol, because there's more of it, right? So just going based on the mole fractions, I have more of my methanol than my ethanol. So that's going to be my solute to my solvent. So for my solute, I need moles. And for my solvent, I need kilograms. So the good news is I already have moles of my methanol, right? So this is my mole fraction, so 0.250% of this is this many moles. So if we just kind of think about this as, you know, 1, then that's the number of moles that we have, so that's good. So we're good to go there, so check. Now we need to figure out kilograms of ethanol. So let's start off with the moles that were given. So 0.750 mole fraction. So if we're kind of assuming 1 of all of this, and we just say, all right, well, 0.25 is methanol, 0.75 moles is this other thing, then we can kind of go from there. So this other thing is ethanol. So I need the molar mass of ethanol. So when I look up ethanol's molar mass, I get 46.07 grams per mole, just coming from the periodic table, right? Adding together each of my component pieces there. So for every 1 mole, I have 46.07 grams. And then I need kilograms because it's my solvent. So everything is per kilogram of the solvent. So I need to go from grams to kilograms. And I know there's 1,000. So that gives me 3.46 times 10 to the negative 2 kilograms of ethanol. And now I can take my moles. Well, I have 0.250 of them, of my methanol, oops, divided by my kilograms, 3.46 times 10 to the negative 2 of my F. The nomenclature here, my kind of symbology here is the prefix, the organic prefix, and then the OH group. So I'm just identifying it as an alcohol. It's just a shorthand way to do it. I don't know if it's that much shorter, really, 'cause simple-wise, but There you go. That's chemist for you. We shorten things by making them longer. All right, so when I divide that out, then I end up with a 7.23 molal solution of my methanol. All right, so I was given fractions of my total, and so I could use those fractions, that ratio, and if I'm assuming that there's one, then I can kind of just go from there. So if I'm assuming I have 100% of my solution, then I have this many actual moles of these things, and then I can figure out that concentration based on knowing which one is my solute, which one is my solvent, and my definition of molality. Now, how does this relate to molarity then? In order to get from molarity to molality or vice versa, I need another piece of information. I need a density. So let's do this conversion here. It's asking for the molar concentration now. So what is the molarity, the number of moles per liter, of an aqueous or aqueous solution of NaCl? That is 3.42 molal. And you're given a density of the solution. So there's a couple different ways that you can do this. The first way that I kind of like to start off is to figure out the mass of the solution first, because if I can get from the mass of the solution, then I can use the density to get to the liters of the solution, right? Because what we need moles of solute, and we need liters of solution. That's what we need in order to get to molarity. So in order to do that, then I like to start with the liters of solution part. So we're given a density, we have a molality. So that means if we unpack this thing, that we have 3.42 moles of NaCl for every 1 kilogram of water. And I know that it's water as my solvent because it tells me it's an aqueous solution. So I know that I have 1,000 grams of water. So I need to figure out how many grams of sodium chloride I have. So let's take those 3.42 moles of sodium chloride and figure out how many grams there are. So we're going to undo this and give ourselves grams by going to the periodic table and finding out that the molar mass is 58.44 grams for every 1 mole. And that gives me 199.86 grams, which would be kind of 200 grams with 3 sig figs. You can round at the end, of course, if you want to. I'm just going to keep it for nice round numbers. So I have 200 grams then of sodium chloride. I have 1,000 grams of my H2O. So my total grams of solution, my total mass of solution is 1,200 grams. So I added these guys together, the 1,000 grams here, the 200 grams here. That gives me this total mass. What I can do with that then is figure out the number of liters, because I can use this density of my solution to go from grams to milliliters, and then from milliliters to liters. And that gives me 0.556 liters. So this divided by my 2.16 divided by 1,000 gives me this. And now I already have the number of moles, right? That's already kind of given to me. The number of moles of solute stays the same in both molarity and molality, right? That numerator value is still the moles of solute in either way. So I have moles of solute already. I've now calculated liters of solution from the density. So I can go my 3.42 moles divided by my 0.556 liters, and that gives me a 6.15 molar solution of NaCl. Again, really intentional with my molarity, molality, but this is big M moles per liter of sodium chloride. Okay, so that's an introduction to molality, kind of how we can go back and forth with the different concentration units. And again, we'll get into the application of molality in a future video when we talk more about what are called colligative properties. In the meantime, if you have any questions, don't hesitate to reach out. Otherwise, I'll talk to you again soon.